Please.
Hmm.
Thank you, sir. Okay, guys, can you see my screen?
Yes, sir.
Okay. So, angular momentum and its application. Okay, guys. So, what is angular momentum? If there is a body which is rotating, it would have a certain angular momentum with respect to a certain point. Is that clear? Given by the letter L. So, suppose I have, and the body itself may not be also rotating. So, I'll just correct my statement. Okay. If there's a certain body, say moving, it's a point body. Okay. M mass moving with V velocity. And I want to study the angular momentum with respect to some point O, which is a fixed point somewhere. It is there. It is O. So this distance from here to there is, suppose it is R. Okay, I'm just having some trouble with my writing pad. Something is happening. It has gone into some mode which I'm kind of liking also. Automatically it is making straight lines and all, but it is little difficult to write. Anyways, now what is the angular momentum? Anybody? Can you tell me what's the angular momentum? So angular momentum is, yeah, M,
To V cross.
guys.
PR.
Yeah, see, it is making some rubbish thing. How to exit this mode? Anybody knows how to use? One second, guys. Okay, just give me 1 second. I'll try to figure out. Yeah, I think it is normal now. You can still see my screen, right, guys?
Yes, sir.
Yeah, okay. M, V, and with respect to some other point, O, it is R away. So angular momentum is M R cross V. Okay. And it is a vector quantity. Now R is which way? From O to V. That means R is this way. And V is obviously given that way. Now, if you have to do a cross product, you should know the angle between them. Is that clear? So, is this the angle between the vectors? Is this the angle between the vectors? Is it? Yes or no? Just say yes or no.
No,
You may right, you may be wrong. Doesn't matter, man. It's not an exam. Yes or no?
no,
No.
Okay. Angle between the vectors is when you keep the tails of the vectors together and the angle what it makes, right? So, this is your angle between the vectors, right, guys? Is that clear? So, you have to lift one of the vectors and keep the tails together. So your angle between the vector is this theta, and your r cross v is your angular momentum. Okay, is that clear, guys? So if you have understood this, just tell me one answer. Very basic question. I hope people are here for the basic clarification only. I'm not doing anything much advanced. The body is gone over here with the same velocity v, and from the same point O, now this is some r dash distance. Okay, that's the vector. The angular momentum has increased or decreased, and what's the reason? Understood the question, guys? Understood the question? Understood the question? Hello?
Yes.
Yeah. So just tell me whether the angular momentum has increased or decreased, and what is the reason? It is going with the same velocity, so momentum is same. Momentum P was mv, exactly same direction and still same. Yes, any answer?
So it'll remain
Any answer?
constant.
It remains same.
Yeah, reason?
So there's no
Absolutely
torque
right.
passing.
Ha, wrong reason, man.
Sir, r sine theta will be same.
I did not say that it has maintained the path because of some force or not. Okay. So I have not commented on all those things. I've just given you two situation and I'm asking you the angular momentum, right?
Sir,
So according to the formula,
r sine theta is same here.
yeah, R cross V. Who are you?
Sir, Janvi.
Same Janvi who was in the previous session.
Yes, sir.
Yeah, 11th or 12th?
11th.
Okay. So yeah, you may be here. Okay, but 11 guys, you are here just as an audience. Okay. Because same thing is going on, but it is for 12th. Okay, this session is for 12th. Okay. So I would say none of the 11th people will answer anything. Is that clear?
Yes.
Okay, is that okay? 11 people, if you want to be remaining here, you can remain here, but you're not allowed to speak. So it is kind of a that's the rule. Okay. In the first session, you can speak, where 12th can join, and 11th will speak. Here, only 12th will speak. Okay, so when we do a R cross V, it is more easily understood as MVR perpendicular. Like this is MRV sine theta, and MVR sine theta is easy sometimes to do, and sometimes V sine theta is easy to do. R sine theta is called the R perpendicular. That means in the line of velocity, if I complete the line of velocity, which is this, whether it was earlier velocity or the later velocity, what is the offset perpendicular distance, or offset I love to call it? What is the line of velocity is how much away from the point in question from where we are taking the angular momentum. So what is this perpendicular distance? So when this was theta, this was your r sine theta, which is r perpendicular. And when this is your theta dash, and this big is your r, theta dash is small, and in the right angle triangle, this perpendicular distance is still r dash sine theta dash. So r perpendicular in both the cases is same. So M is same, B is same, R perpendicular is same, hence angular momentum is same. Okay. Which might be same because okay, there was no torque. I can agree to it in a way, but that is not what I was asking. Is that clear, guys? So that's the angular momentum of a point body. Is that clear? Angular momentum of a body, extended body, which is say rotating about its center of mass, as well as with omega, as well as going forward with V, and omega has it has got no relation with V. Okay, it may be spinning very high and going forward, it may not be spinning that high and going forward. It may not have a spin at all as the previous case and going forward. Okay. And if I want to study from a point here, O, at a distance R, so what is the angular momentum now? So angular momentum formula now would be L is equal to, first of all, it doesn't see the whole body, it just see the center of mass and carries forward with the earlier formula of R cross V. Okay, but then it is not only the center of mass which is going forward, it is the whole body, the other parts. So other parts are having an angular momentum about the CM. So how much it is about the CM? It is ICM omega. Okay, and it's a vector addition. Is that clear? Is that clear? Is that clear? In this particular super easy cheap case, your omega direction and R cross V direction is same. Okay, now you can't see my thumb and all, but I hope you know that if you have a R this way and a V this way, and I have to do a cross product, then R cross V will go. You have to rotate your fingers from R towards V, and the thumb, right hand thumb rule, it is going to point inside. So that's your R cross V direction. And omega direction, you have to curl your finger this way with omega, and your thumb is still going to point inside. So omega direction is same. So you literally add it up. Okay. Is that clear, guys? Is that clear? Is that clear?
Yes.
Yes, sir.
Okay. So I'll ask you a very cheap question, not so cheap question, and you have to answer it. Okay. Okay, I'll just complete this part. Now, after some time, the body has gone over here. And it was obviously rotating, so it may be in this position now. Rotating with the same omega. And is still going forward with the same velocity as earlier. So it is swirling and going. With respect to this point, now, has the angular momentum increased or decreased or remains same? Class 12, has the angular momentum increased, decreased or remains same?
Remains same.
Class 12, you are?
Yes, sir.
Yeah, it remains same because MRV remains same as discussed earlier, right? And since omega is same, ICM is obviously ICM, that's a constant for the body. Through the axis it is rotating, and omega is same, then omega is also same. So both the parts remain same. So yes, it remains same. Is that clear? Get the point? So we can always imagine if this body was not having any torque, it would have gone with the same velocity without changing velocity, and it would have rotated with whatever it was rotating. That means you have thrown a certain stick in space with this velocity and this omega. It will keep on going with the same omega and velocity and keep on going. No torque on it. Is that clear? Is that clear? Now let us take a real one. Let us just take a real one. A real question. So there's a stick, and at the end of the stick there is a wheel. Okay, like this is the axle of the wheel. Is it kind of clear, guys? And then it is rotating omega like this. Okay, is that clear? Find the angular momentum. So mass of the stick is m, length of the stick is l, mass of the wheel is capital M, radius of the wheel is r, and it has got a moment of inertia I is equal to, it is kind of a ring, it is mr square. Okay, that's the moment of inertia. Is that clear? spokes are very light and the whole rim is having the weight. And along the axis, it is mr squared. At this moment, drawn on the page, what is the angular momentum? Is that clear? Now, before you do the question, I think I should have done one more theory part. So I'll just do it very fast. If a body is rotating about a fixed point, like this one, the body is freely rotating about cm and the cm is going forward. So it is like, it is not having a fixed point of rotation. Versus, suppose I have a certain, say, that a certain shaped pendulum and it has got a fixed point of rotation. Cm is somewhere over here. This is the Cm. This is the Cm, and this is a fixed point of rotation. Okay. What is the angular momentum if it is rotating with omega? One is the old way of doing it. I'll find out how much was the velocity using my omega into r, omega into this r. I'll find out the velocity, and my formula of L is equal to m r. This is your r into v, which you will find out using your omega, which will be omega r. So that's the first part of the formula, plus ICM omega will remain. This, nobody can change this formula. But we can use another one over here. What the other one? The other one is I about the fixed point of rotation into omega. Both will come same. When we do the calculation, both is going to come same, okay? Because as you can easily see, this V can be written as R omega. So this part will become your mr square omega. And then there is the ICM omega. So if I take omega common, it is mr square plus ICM. And mr square plus ICM is nothing but Ix using parallel axis theorem. So anyways, the point over here is either you can use this formula, or if there is a fixed point of rotation, then you can find the moment of inertia about that point of rotation. And so much into omega is also a formula. So your wish, you can use any of it. Okay. This formula is valid all the time. It is only valid for fixed point of rotation. Okay. Now, anybody? Somebody for the rod? Can you tell me for the rod? L for the rod. L of rod. L of rod. L of rod. L of rod. Anybody?
So is it ml by 3 omega?
Absolutely right. You could have. You're using this formula, right? This one.
Yeah.
So it has got a fixed point of
Confused
rotation.
which one is the fixed point?
There's a fixed point.
Oh, okay.
Yeah, it's going round. I hope you are understanding how it is going, guys. because I'm not able to show with my hand. It's going flat and round. This is the ground, okay? Is that clear? So this guy, this wheel is coming out of this wheel has got a velocity which is out of the plane. It is coming out of the plane. Is that clear? So L of rod, by two ways I could have done it. One, fixed point formula. So that is very cool because it has got a fixed point. The formula is Ix into omega. How much is Ix of the rod? About a side point is 1 by 3 ml square is your Ix into omega. Is that clear? I could have used my old formula. What's my old formula? Which I'll not recommend to use in this case, but you may use it. Which is, where is it gone? Which is this one. Okay, what is that? First, you see only the center of mass and nothing else. So I'm just seeing the center of mass and nothing else. And I'll write m v r. So what is the velocity of the center of mass? Center of mass is L by 2 away from the fixed point. So its velocity must be equal to omega L by 2. Any doubt? And then that velocity mvr is how much away from the point in question? It is L by 2 away. mvr. mvr is the first part of that formula, right? Second part of the formula is you sit in the center of mass and observe things. So ICM for a rod is 1 by 12 ml square. Right, guys? Right, guys? And omega. So once you sit over here, cool part about a rigid body is if omega was about this point, then you be anywhere on the rod and the rod is rotating about that point with the same omega. That's the coolest point. You don't have to think about some other omega. If you have doubt on that, I will clarify that separately if you ask a doubt. Okay. If I do this calculation, obviously it will come as m L square by 4 plus m L square by 12 omega. To do this, it comes as m L square by 3 omega, which is same as what you got over here, right? Is that clear? Is that clear? I would say this was much ado about, obviously nothing which is quite fast. Now what about the wheel? Who can say that L of the wheel? Guys, anybody any doubt on this L of this? How did we do? Either this or this part, any doubt? Take a snapshot of this window because today we are just doing how to calculate angular momentum. Next we'll do how to use angular momentum. Conservation of angular momentum. Today we are just calculating angular momentum. So L of the wheel, guys, anybody? L of the wheel? Anybody? Now I will try to use my MVR perpendicular. Okay. Because I'm really skeptical and ICM omega. Is that clear? So when I use MRV MR cross V, I see only the center of mass. So the best part is I'm just seeing the center of mass. I don't care whether it was a wheel or whatever. Center of mass is here. So what is the mass? They have given the mass is capital M. Then R means how much it is away from the point in question. It is how much away? It is, I'll write in green. It is so much away from the point in question. How much is that? It is L away. And what's the velocity? For sure, it is coming out of the plane, and the velocity must be equal to omega L. Is that clear? Is that clear? Omega is the rotation. Any doubt in this part, guys? Any doubt in this part?
No, sir.
No,
No.
sir.
Okay. ICM omega. Now I'm just sitting on the wheel and I will check out that, okay, this wheel is having what ICM about the axis? Okay, it is given that the ICM is mr square. Very good. What is the omega? Now this omega, and I'll call it omega dash over here, is not that omega at all. It is how fast it is going round and round. So there a little bit of physics and maths is going to come into picture. Okay. If there is no slipping happening and the velocity of the center of mass was v, if this velocity was v, then your omega dash must be equal to v by r. Right, guys? Right, guys? And the v was how much? V was omega L. So omega L by r. Think about it. Okay, if you have any doubt, you ask me. So ICM omega becomes m r square omega L by r. This is this part. This is this part. So I'm just going to make it little more tidy and write it as m L square omega, and this part I'm going to write it as m r L omega. Is that clear? And can you see I'm not putting a plus over here and I'm really being careful over here. Can anybody tell me what, why, what am I doing? I'll put a plus. I'll put a plus, but I just wanted to be a little technically right, and hence I was not putting. I'll put a plus now because I'm going to do something else and put a plus. So why am I not? I'm not putting a plus very easily. Here I put the plus very easily. I didn't even make you think that we don't have to do a 1 by 4 plus 1 by 12 and all. I just do the plus very, very easily. Here I'm not doing the plus. Can anybody tell me why? Because I've not written the directions, and the directions unfortunately are not a simple plus. R cross V will be what in for the rod? What will be the R cross V? That means this is your R. Oh, sorry, not for the rod, for the center of mass of the wheel. R cross V. What will be the R cross V? Tell me, guys. Up, down, outside the plane, inside the plane. The body, this velocity, this body is coming outside the plane. So what will it be? The rotation is happening like this. I cannot show my face. Anybody? Anybody? That's the tricky part in this question. What is it? R cross V. It is down. Why it is down? You can curl your fingers with the movement of how the rod is going or how the red dot over there is going. Okay. So R is this side. That's your R vector. And V is outside. That's your V vector. You curl your finger from R to outside, you'll get a down. So this guy is so much down. So if I define this as my I, this as my J, and outside as my K, then I got a minus J. So this is a minus J to it. Then I can write a plus properly. Okay. And what about this side? What about this thing? Anybody? Can you give it a try? MRL omega. So this was in the direction of omega. So what is the omega direction? The wheel is spinning this way. If you curl your finger that way, as the wheel is spinning outside, your omega direction comes this way. That's the omega direction. What is that direction? That's the I direction. So this is the I direction. Hence, the answer is minus ml square omega j plus mrl omega I. Now, since there are two vectors which are 90 degree to each other, one is this way, one is this way, the net answer is this plus this, that means this is the net answer, which is equal to under root of ml, and omega is common, so I'll just put it outside the bracket. Undo. M is common, L is common, omega is common, under root of L square, and from there R square. That's the value of L only for the wheel. Obviously nothing to do, this part is nothing to do with this answer. In this answer, you have to write the direction of the rod also. So rod was going out. So if the rod was going out, I'll curl the finger in the omega direction, this omega direction, and I will get downwards. So minus j over here is the direction. So total L, net L of the rod and the wheel was, you have minus j due to two things. So due to ml square by 3 as well as capital M L square, omega. So minus omega j, and due to the wheel, cm of the wheel, it was mrl omega I. So that's your total answer. So you do a square of this plus square of this, you get an answer. So that brings an end to how to use your angular momentum straight away if they ask you what is the angular momentum of a certain body. Now, if you have any doubt, you ask me. Those who don't have doubt, they may go away. Next class, you tell me what to do. Otherwise, we will do a question where we are conserving angular momentum of a body which is trying to pure roll. Is not pure rolling, but it achieves pure rolling after a certain time. This is the
Sir,
next class agenda. Here you tell me what to repeat, what to do, and I'll do that.
sir,
Yes,
can you once again explain the omega dash finding?
omega dash. Yeah, cool. Yeah, I really wanted somebody to say that. Thank you for saying. Can I just share my face because I have to show with my hand? Because I'm just fearing that some of you might not be knowing that how it is looking. My drawing is not going great over here. Stop sharing. Okay. To share my face, I have to stop sharing the other screen. One second, guys. Okay. So this was the rod. Can you see this, guys?
Yes, sir.
And that's the wheel. Is it also visible?
Yeah.
Only kind of wheel. It's black, so it will not be very well visible, but I hope you can make out something. And it was going around like this. Is that clear? So when it is going round on a ground, So the wheel is rotating and going round. It is rotating and going round. Okay, it's rotating. Can you see? Is that clear?
Yes, sir.
So first thing about the rod, since the rod was going around like this, okay, I'm making it, there it was going this way towards my face, okay? But in the camera, it will be easy for me to show this way, okay? So if it was going around like this, if I curl my finger that way, it is upwards, so plus J direction. If it was going towards my face, then if I curl my finger that way, it is downwards, right? If it is going towards my face. Is that clear?
Yes,
So
sir.
that is why you are getting ml square by 3 into omega downward direction. Is that clear? Now when I talk about the wheel, so the rod is no more in question. From this point, this was again coming towards my face because the rod was coming towards my face. So first I see the center of mass of the wheel. Center of mass is coming toward my face. So I'll again curl my finger, which again goes downwards. So center of mass MRV was coming downwards. And what was MRV? M was the mass of the wheel. R was the distance from the point of question to the wheel where it is, the center of mass of the wheel where it is. So that was L. MRV. So M, capital M into L. And what's the velocity? The velocity would be whatever the tip of the rod is having the velocity. So because center of mass was at the tip of the rod. So the rod was rotating with omega. So tip of the rod was having the velocity of, one second guys. So tip of the rod was having a velocity of omega into L. Right people? Right people?
Yes, sir.
So the center of mass of the wheel had an angular momentum of MRV as ML into omega L. Capital M into L is the distance into velocity was omega L. So ML square omega. Is that clear? And the direction was again downwards. Now comes the last part, the trickiest part of this is the wheel was not just a point body going just towards my face, it was revolving and going, right? It was, sorry, rotating and going. Is that clear, guys? So how fast it was rotating. So now I forget about everything else and I just say that it was on the ground and rotating and going towards me, right? So what must be this omega? Then comes my previous class. We had done pure rolling. Suppose it was pure rolling and rotating. Okay, nothing given, then it is pure rolling and rotating. Okay. So if it is pure rolling, then the velocity of the center of the wheel should be related to the omega of rotation, right? And what is the relation? What is the relation?
V is equal to omega.
Velocity is equal to R omega, right? Right, guys? Right, guys? Velocity is equal to R omega, right?
Yes, sir.
Any doubt? So what was velocity? Velocity was omega L. That omega L of the rod was the velocity. Is that clear? Is that clear? Velocity of the center of the wheel was omega L. And if the rotation velocity, I call it as omega dash, then it is equal to R omega dash. So omega dash was omega L divided by R. I can explain again also, okay, if you want. Got it, or shall I tell or ask your questions on this? Got it? The person who was asking?
Yes, sir.
Sure. You have any doubt? You ask me freely. Okay, then we can stop recording. So next session, tell me what should it be? People, next session. Oh, I'll do this. I'll bring an end to this rolling and this angular momentum and then something else altogether. So what can that something else be altogether? Any particular thing you want? I can go slow also if you want. Any particular thing? Yeah.
They link kinetic energy to rotation, right? Could you explain that?
Kinetic energy and rotation. We are not done. Okay, we'll do it next class. Okay.
Yeah.
So that would be end of rotation. Okay, because these are the basics of rotation. Okay.
Yeah.
So
Okay. So,
for 11th grade, so what's the next topic? Next class.
ask me what do you want? Tell me.
So can you do calorie with me, like advanced question? Not advanced, like really complicated question.
No. Very simple things I have to do in 11th.
Very simple.
I'll have a advanced concept daily session separately. Okay.
Okay, so
Simple stuff which you have not understood, you can ask that. Who are you?
Sanjay,
Which batch?
batch 1.
This is particularly for the students who are not understanding. Okay.
Okay, sir.
Yeah.
So what
you
about
want something
electrode
advanced? Huh?
electrode processes in redox?
Electrode
processes like
No.
electrochemistry.
That will do. Electrochemistry, that will do in redox next year. Okay.
Okay, like the basics we are done this year.
Yeah, theoretically you can do. There are few things where if you know the potential, working out the potential, it is better to get the overall picture. Okay.
No, like
So
so
whatever,
using the available and free energy to find out.
yeah, whatever sir has done, that is okay. In the concept time, I'm not going to teach that.
Okay, sir.
Yeah. Okay. Hello. Bye.
Yes, sir. Thank you.
Thank you.